Welcome back to class module 3.1, Thermodynamics of Electrochemical Cells. That's what we are going to look at in this module 3.1. We'll look at introduction, we'll look at standard Gibbs free energy, that is delta G naught for a cell. We'll look at equilibrium constant for an electrochemical cell, some illustrations, and we conclude. Introduction. Electrochemical reactions involve the movement of electrons. They can use voltaic cells which proceed spontaneously, have negative values of free energy, large self-potentials, and large equilibrium constants. Electrochemical reactions can use electrochemical cells which must have an energy source to proceed. Therefore, we now want to find out how we can predict the spontaneous direction of a redox reaction. So we want to find out our ability to predict if a reaction can go on as written or can go in the reverse direction. We also want to find out how we can calculate the cell potential at standard conditions and non-standard condition, and then how we can derive the relationship between equilibrium constant and Gibbs free energy of the reaction. 1. The change in standard Gibbs free energy for the reaction. This is given by this equation 1, delta G naught is equal to NF delta E naught. N is the number of electrons transferred, F is the Faraday. Remember, we have met 1 Faraday, that is Na multiplied by E. Na is Avogadro's constant multiplied by the charge of an electron gives us Faraday constant, and delta E naught is a change in the standard E naught, that is electric potential of the cell. If not under standard conditions, we still have that delta G is equal to minus NF delta E. Thus, delta G is negative if delta E is positive. Look at it here. There's a minus here. If this becomes minus, then this becomes positive. If this becomes positive, then this will be minus. And if delta E is positive, that makes delta G negative. This means that cell is operating spontaneously, that is feasible and spontaneous. When delta E is negative, that means the negative here cancel the negative here and make delta G positive. The delta G will be positive, and the reversible reaction is feasible. Now, if delta E is 0, then automatically everything on the right hand side here becomes 0. That is, delta G will be 0 and the cell is said to be at equilibrium. Deduction from what we just said. The negative sign on the right of that equation 1 indicates that the positive cell potential implies a negative free energy change, and thus that the cell reaction will proceed to the right. That's what we've said. Electrical work is done when an electrical charge Q moves through a potential difference delta V. The right side of equation 1 refers to the movement of n moles of charge across the cell potential E naught, and thus has the dimensions of work. And the Gibbs function is more than a criterion for spontaneity. We have used it to check the spontaneous nature of the reaction. So we're saying is more than that. It can also express the maximum usable work that the system can do to the surroundings. And we're talking about PV work here. So that is also the practical use of this change in Gibbs free energy. Therefore, the maximum work can only be extracted from the system under the limiting conditions of reversible change, which for an electrochemical cell implies 0 current. means that the more the cell operates, the less electrical work it can supply. If F is expressed in coulombs per mole, remember our Faraday, the electrical work delta G naught is in joules per mole. So we're trying to relate these electrical units. Remember we mentioned it at the beginning in terms of coulomb or power or work done, and of course as current is measured in amperes. Number 2, we have looked at delta G naught. Number 2 is the equilibrium constant K. Now if you have this reaction, that's equation 2, the change in Gibbs energy will be this. Remember we made this equation before. This entire x, y, a, b here gives us equilibrium constant. Therefore at equilibrium, delta G, which is this, will be equal to 0. So when this moves over to the left side of the equation, we will have delta G naught equal to minus RT ln K. And this equation is very, very important. Now let's give an example. If this is our cell between hydrogen and copper half cell. Now we have that delta G naught is equal to NFE, and also delta G naught is equal to this. So we can equate the two, and when we equate and make E the subject, we have equation 4. RT ln K all over NF. Now if we put the values, remember R is a constant. If you put temperature, room temperature at 25 degrees C and Faraday, and then this gives us equation 5. Of course, if we still use zinc and copper, that is our Daniel cell, we will still obtain the same relationship. Here we have illustration 1. Calculate the equilibrium constant for the reaction. We are given the reaction, we are told to calculate the equilibrium constant. We are just, using what, applying what we have learned. We'll try to write this is equation. We'll try to write the equation out, balance the equation, and check the change in E naught value. That is the E naught for the cell, and number of electrons transferred. And we'll use this our equation here and find the value of K. The second illustration is also here. These are the equation that is given. We find the E naught value, E naught 1, E naught 2. So we want to find out delta G1, delta G naught 1, and delta G naught 2. We supply it to our equation. Delta G naught is equal to minus NFE, and then we find the E naught for the reaction. Thank you very much. We have looked at delta G naught for a cell, equilibrium constant for an electrochemical cell, and some illustrations. I hope to see you in the next class, as I hope you enjoyed the class. Thank you.